Hi, welcome back to Math 533, Topics in Euclidean Geometry. In this, our last video for week 8, we're going to talk about one last example of an isometry, something called a glide reflection, and then we're going to talk about a beautiful theorem that classifies all of the Euclidean isometries. So let's start with this definition of what's called a glide reflection. The idea of a glide reflection is that we take two isometries that we've already talked about. We take a translation from A to B, and we take the reflection across a line and combine the two of them in order to get a transformation. Right? So we compose these two isometries, the translation and the reflection across the line AB. Right, so the interesting thing is the translation has a vector here from A to B, and then we also use that same line for our reflection. So here's a picture of it. I have here AB. I made them nice and far apart so we see a lot. And I have here my triangle UVW. And what I imagine doing is I imagine translating it over here-ish, and then I reflect it over the line AB. And so that gives us this U prime V prime W prime. Okay, now that we have a glide reflection, we have this beautiful classification theorem of all of the Euclidean isometries. And I should mention, in the literature, an isometry of the Euclidean plane is also often called a Euclidean motion. So the theorem is that every Euclidean motion, or every isometry of the Euclidean plane, is one of the following items. It can be the identity, so it's a really boring one. It can be a rotation. We talked in our previous video about rotations. Notice that there are infinitely many rotations, right? I can choose any number of the infinite points of the plane to be the center of the rotation, and then once I'm there, I have an infinite number of angles I could rotate by. Okay, and then the next candidate is my isometry can be a reflection, right? And again, there are infinitely many reflections because the plane has infinitely many lines in it. We can have a translation, and again, there are infinitely many possible translations, but still and we saw in the previous video about what a translation is. And then the last possibility is we can possibly have a glide reflection, which is the example that we just saw. And there's nothing else. There are no other isometries that are not on this list that I have written down for you. Everything is one of these. And arguably, the identity is a rotation with the zero angle, or a translation with the zero vector, right? There's nothing wrong with that perspective if it makes you happy. So we're not going to prove this theorem in our class, but instead I'm going to give you a sketch of where the idea is coming from. And there's basically one step of the proof that's a little bit involved. If you're really excited about it, I can post a proof for you to read. But the idea is to leverage our theorem from last week that every isometry of the plane can be written as the composition of 0, 1, 2, or 3 reflections. And in this case, we're just going to break down by how many reflections we needed. Okay, case 1. We have 0 reflections. Well, 0 reflections means we're the identity. Good. One reflection means we're a reflection. Also good. If we have two reflections, there are two possibilities. Either we're reflecting with a pair of intersecting lines, or the two lines are parallel. Okay, if they intersect, then the two reflections are going to give us a rotation. And actually, we can even say what happens in this case. And if I have a pair of lines that intersect like so, we're going to get, well, if they don't intersect at 90 degrees, we get a pair of vertical angles here where the angles are acute, meaning they're pointier than 90 degrees. And then the rotation is going to be by twice that angle. So that's very nice. And of course, if they meet at right angles, you're doing a rotation by 180 degrees. Okay, and then two reflections, that's going to give a translation if the lines are parallel. That one also is going to follow from the work we just did. The hard part of this theorem is proving that an isometry that is the composition of three reflections is a glide reflection. Right, a glide reflection, just the way we defined it, we're thinking of it as a composition of reflections with two lines that are parallel and then a third line that is perpendicular to both of those guys. So there's some work involved where you can take any three lines in the plane. You have the reflection about the composition of those three reflections. You take those three lines in the plane and you maneuver it so that you can fix it to make two parallel lines and one that's perpendicular to both of them. Right? So that's the hard part of this theorem, and it's something you can go and figure out with a bit of work. But we're not going to do that. Okay, that's it for the classification theorem of Euclidean motions. And that's it for this week. I'll see you on the next one. Happy mathing. Thank you for watching.